Okay, so this is homework 4, part A. I'm going to be working on A1 during this portion of the video. And this is the highlighted section. Over there on the right, I have two tanks, each with a cross-sectional area of 2 meters squared. And flow rates coming out of each of the holes is 2 times the height square rooted. And then we also have 3 different streams coming in. So I will be calling this is U1 and it is equal to 2 meters cubed per second. This is U2 and it is equal to 0.5 meters cubed per second. And then down here we have U3, which is equal to 0.4 meters cubed per second. And then we do have this right here, which is, let me make that a little bit bigger. We have this flow right here, which is Q2. And we have this flow, this is Q1, and we have this flow right here, which is Q2. And Q1 and Q2 will help us find, those are in relation to the height of the tank, which I have over here. This is H1 and this is H2, height of the liquid inside the tank at any given time. And in my previous videos I've stated how we get to that point and how we do the change in time, or the change in volume in respect to time. So I'm just going to put that here. As always, we're going to start with that simple equation of Q in minus Q out. And a more complex version of this we're going to have 2 equations. We want to have one for Q in, or one for Q1 and one for Q2. And with that, for a steady state, we're going to need an initial for U. And that'll come later in the coding portion of this video. But essentially, we're going to have, and then we also, the area of these holes is 2, the cross-sectional area of these holes. So I'm going to put that, right here. That's just AC equals 2, and right here we have AC equals 2. So essentially with this equation, we have AC times D H, I'm going to make that lowercase, dH dt equals U1 plus U2 minus Q1. And then we also, and this is simplified down to dH over dt equals U1 plus U2 minus Q1 divided by AC. And then our next equation we have is AC times dH over dt equals Q1 plus U3 minus Q2. And again, this will simplify down into dH over dt equals Q1 plus U3 minus Q2 divided by AC. So since we're just finding the steady state, it's relatively easy. This is all the equations we'll need for part A1, and I'll go ahead and code this portion of part A. Okay, this is part 4A of homework 4. And in this portion of the coding video, I will just be coding the previous equations that I had worked out. And this is just to find the steady state of the level inside the tanks at any given time. So first we're going to start out with just our variables, and we have AC, which is the cross-sectional area of the tanks, which is equal to 2, and then we also have alpha, and that is also 2. Equals 2. And then we also have our flow rates, and we have flow rate U1, U2, and U3. U1 and U2 going into tank 2, and U3 going into tank 2. So we will define that in terms of an array. So I will call that I'll call that U in, and that is equal to J and P dot array. And I believe, let me look at the numbers. So we have two, 0.5, and 0.4. And that's our array. And then next we're going to jump right into just defining the right-hand side of that equation. So define right-hand side, and this will be in terms of time, height, put this in here actually, and oh gosh, time, height, and flow rate. So below we are going to define what height and flow rate is. So that would just be the H and the U. So we'll have, since there's two tanks, there'll be H1 and H2, which is equal to just H. And then we also have U1 going into tank 1, we have U2 going into tank 1, and we have U3 going into tank 3, and this all equals U. And then I'm also going to define Q in terms of flow. So Q is going to be defined as the flow rates out of the tanks. So we'll have, again, U1 and U2 going into tank 1, and then Q1 flowing out of tank 1. Then we have that same Q1 and U3 flowing into tank 2, and then we have Q2 flowing out of tank 2. So Q1 is just equal to alpha. I'm gonna uncapitalize. Oh. Alpha times H1 square root of 0.5. And Q2 is just the same, but with H2. So alpha times H2 square root of 0.5. And then here we can just return this, and this will be the equations that I worked out in the previous section of this video. So we first have, let me make sure I have this right. Okay, so we first have this as Q1 plus, oh, not Q1, sorry, U1 plus U2 minus, this is in an array, There we go. Okay, u1 plus u2 minus q1, and I'm going to put this in parentheses. And this is divided by AC. And then we have q1 plus u3 minus q2. Oh, man. Minus q2, and then divided by AC. And we will return that. Oh, to close this. Awesome. So then we will go to solving this. So we will do root, and then lambda, lambda. This is actually lambda x, and then right hand side, we have 0 dot, 0 dot, comma, x, u in with 1, 1. And we'll return that. Oh my goodness. Oh, I forgot to put these in parentheses. What's it's yelling at me about? There we go. Okay. And these right here, this x is what is the height at this time. Okay, this is part A2 of homework 4. And here what we are trying to accomplish is, turn this a little bit, is we want to use the Jax function to linearize the equations, the dynamical equations, basically the ones relating to the ones that are like the q in minus the q out, and we want to relate those to the input and output variables, which is basically h1, h2, and u2, u1, u2, and u3. So we'll first start with just a basic Jacobian function. And basically it's just a simple matrix. A Jacobian is basically just a function that is needed, a function that incorporates two other functions. So it looks something like this. So we have J, and then we have our matrix. And here, so we'll start with our partial function. Something will work. Yeah. And we have F1 on top for both. F1 in relation to X, and then in relation to Y. I'm gonna make it focus. And then we have partial function of F2 on the bottom in relation to X and Y. So we have this function in relation to, and we want to expand this. And so with this expansion, it comes at a certain point of the expansion of what we want this to happen. And at this point, we want it to happen at the steady state. So our function will look like this. We'll start with h, and this is just equal to our dh1 over dt, and then dh2 over dt. And this is approximated to be, so we'll first start with, and this is relation to j, H. Our H equations are our H1 minus H initial and H2 minus, oh, this is H1 initial and H2 initial. And this will be added. So we also want to find it in relation to U. So we'll have JU. And this will be the same thing. We'll have U1 minus U1 initial, U2 minus U2 initial, and U3 minus U3 initial. So we will use these Jacobian functions with our current code that we have to find the relationship between the output and input variables, to linearize them. So. Okay, then we go over here to our code, and first we want to set this root. This is our H initial, so we've already defined our U initial up here in this array. So we also need to define what H initial is in order to work out this Jacobian. So we will set this equal to initial and make sure we call out that we are specifically looking for the x in that function that it called, or that it equaled to. And then down here we will start with our JH function. And this is equal to Jax dot Jacobian, the right hand side, and 1. Note that this 1 is in relationship to these values right here, these variables. T, if we were wanting to find this in relationship to time, we'd use 0. And then, so T is 0, H is 1, and U is 2. And so right here, since we were trying to find H, the relationship with H, we're going to call out number 1. Then we're going to define our JH. And that is equal to the JH function. And we're going to call out the variables that we want. So this will be our H initial and our U initial. And then we will just call out our JH. Perfect. Okay, so these numbers right here. So this number, this 0.4, is basically this first equation with respect to H1. This 0 right here is this first equation in respect to H2. However, notice that it's 0 because tank 1, this is the equation for tank 1. Tank 1 does not rely on the height of tank 2. So that is why this number is 0. Then this 0.4 is this second equation in respect to H1, and this is not 0 because the height of, the liquid that is inside tank 1 goes into tank 2, and that determines the flow and the height of tank 2. So that's why that is not 0. And then this number right here is the second equation with respect to H2. And then I'm actually just going to copy this and I'm going to put it down here. And I'm going to change this to JU. I'm going to change this to 2 since now we want to call out the U function. And I'm going to change these all to JU. Now, since this has 3 equations, this will no longer be a 2x2 matrix. It will now be a 3x2 matrix. So it would be 3 across and 2 down. Just like that. So these first two 0.5s are this first equation with respect to U1 and U2. And again, this 0 over here is that first equation in respect to U3, and it's 0 because tank 1 does not have flow U3 coming into it, only tank 2 does. So that's why when we come down here, these first two values are 0 because that is equation 2 with respect to U1 and U2. And unlike the height of, so back to the height function, even though like the height of tank 1, so the height of tank 1 is a function, the height of tank 2 is dependent on the height of tank 1 because they're flowing into each other. The reason this one does not depend on that is because it is the flows coming in. So U1 and U2 flow into tank 1 and U3 flows into tank 2. So it's very independent of each other, which is why these numbers just don't overlap. And that is the Jacobian for problem 4A. Okay, we are back with part A3. And I left up this part from A2 because for me, I think it's definitely a continuation. But A3 basically wants us to use scipy.signal.statespace to obtain a linear time invariant representation of the system. And we can do, and it wants us to isolate H2. And to do that, we basically can just set this, so we set this y equal to 0, 1, and then the matrix H1 over 8, oh, I do not need that, H2. So here, it's basically doing 0 times H1, which is 0, and 1 times H2, which is H2. And then we're going to add this. So we also have to not only isolate it from, not only isolate H2 from H1, but we're also isolating it from U1, U2, and U3. So we're going to add that, and we're going to put in 3 zeros. And then we're going to put in the matrix U1, U2, and U3. So this basically isolates H2 from everything else. So, okay, so back to part A3, the coding portion. We want to put this in terms of a linear time invariant. And that we can do by calling out LTI system equals sig dot state space, and then this is going to be in terms of the array AB with A, B, C, and D. So our A is just going to be our JH, which is our Jacobian that we made before in terms of height. And then we have our JU, which was our Jacobian in terms of the flow rate U. And then we have our first array that I had made in the previous portion, which was the 0 and the 1. The 0 that canceled out H1 and the 1 that called out, that like isolated H2. So I'm going to put that in as np.array. And then that is just 0, 1. And then I am going to do the next array, which was to cancel out all of the U's, so U1, U2, and U3. So again, that's just an array. Array, and that is 0, 0, and 1. I'm actually going to put periods behind all these just to make sure that it's a hard 0. And then I can just call out this LTI system, and it should give us back our array for only H2. Okay, so here we have part A4 of homework. And for this part, we are wanting to use Google Colab to transform the state space model that we calculated from A3 into a transfer function between H2 and U3. And then I'll write this down as a transfer function after I get the numbers from the array in our code. But first, I just wanted to show what a transfer function would look like for this. So we would have H2, equal, and coefficients on the top be equal, or the coefficient on the top will be n, the coefficient on the numerator and denominator. So we will have n1 multiplied by s squared plus n2 multiplied by s plus n3. This is all over d1 times s squared plus n2 times s plus, d2 times s plus d3. And this is all multiplied. So here we want the transfer function between h2 and u3, so this will be multiplied by u3. So without doing coding, this would be a very difficult transfer function to solve. It would take a really long time, and just not knowing all of the coefficients. So that's where coding it can help make this so much simpler. So we'll go over to the coding now. Okay, so now we're coming over to the coding portion of this. Sig.ss to function, and then we're going to just copy and paste this whole thing, and we're going to input that into here. I don't need this many parentheses. So right now, if I would go ahead and shift enter this, it would show up like that, but this would be in relation to U1. And the question wants us to do this this transfer function in relationship to U3. So to do that, I'm just going to, I'm going to get rid of this. And then here I'm going to input equals 2 is input of 0, U2 is input of 1, and U3 is input of 2. So I'm going to put in input of 2. Okay, so if we then go here, I'm going to write this answer into a transfer function instead of this one that we have up here. So we first would have H2, which is equal, and then to that first number, 0 times s squared plus that second number, that's 0.5 times s, and that second number plus 0.2, and then all over 1 times s squared plus 0.745 times s plus 0.137, and then this would simplify down to H2 equals 0.5 s plus 0.2 over s squared 0.745 times s plus 0.137. Oh, and then multiplied by that u3. And there we have it. Okay, so here we have section A, part A5 of this homework. Yeah, A5. And here what we want to do is compare these the graph of this transfer function, the way we've been doing it throughout this entire code, versus how we would do it with Solve IVP, and the difference in those graphs. And there will be a difference in those graphs, and actually the Solve IVP will be more correct, but this way of doing it with the transfer functions can test the stability of the entire code and just the two tanks in general when it comes to the two heights. So to plot this first, we need a numerator and a denominator for those transfer functions. That's where like I had n1, n2, n3, d1, d2, d3. So to do that, I will be setting this function equal to numerator and denominator. And then I'm going to name our transfer function h2u3. Transfer function is equal to sig dot transfer function numerator denominator. And then down here we will turn this into a step function. So we need to do the variable t. So this is in terms of time and our height deviation variable. And this is equal, equal to h2 u3 tf dot step, because it's a step function. And then we'll do our simple figs like we did before. So fig equals make subplots, and then we have fig dot add scatter with t equal, x equal to t. We have y equal to, so this goes back to our Jacobian transfer function, or like the Jacobian matrix that we did, where our equations for that was h2 plus h initial. So not only will this be y equals h, it'll actually, or h2, it'll actually be h2 deviation variable plus h2 h initial. And then we also have to, we don't want just h initial, we want it to be in terms of h2, so we'll need to put that in here as well. I keep getting mixed up with these. h1 is equal to 0 and h2 is equal to 1, so this is actually 1, not 2. And perfect, there is our graph for the transfer functions. And next I will be doing it for the solve IVP. Down here. Not dot. We have linspace. Oh, sorry, this is np dot linspace from 0 to 20 with time 100. Then we will call our h1, h2 equals res dot sol t plot. Okay, and then we'll start with our figs. Fig equals make subplots fig dot add scatter, where t equals, I keep doing that, x equals t, y equals h. So we're going to put in the linear and the nonlinear functions of this, or the graphs, just so we can see them side by side. And so this is for the transfer functions. So this equals h2 div plus h initial, and then this, oh, and this is in reference to U2, and we will name this linear. Then we'll add another fig dot add scatter, where x equals t plot, no, t, and then y equals h2, and then the name this will be equal to non-linear, and then we want to do fig dot update layout or layer, and we will have the width equal to 600. We'll have the height equal to, height equal to 400. We'll return that. Oh, it's layer. It's layout. How do you say layer? Layout. Oh, what? Layout. Oh, I don't know why I did that. I don't need these right here. And then, okay, I think everything else is, oh, this needs to be t-plot. I think that is also causing issues. Okay, perfect. So there we see this blue line is from our transfer functions and the red is from solve IVP. Like I said, the solve IVP is actually more correct. The transfer function is just used more for stability of the entire process. So when doing this in real life, or as trying to actually find the heights of tank 1 and tank 2, we would use the solve IVP, and this is the graph that shows it.